if people want to get down into this really far, go to our
Uh-huh.
website and pull up the white papers. They go as
Right,
deep as they want
right.
because those are somewhat self-explanatory if you understand the
Hmm.
technology and the English behind that kind of a
Yeah.
vocabulary. So,
Well, I'm looking forward to this. I've made a lot of progress personally in my enthusiast level understanding of all this stuff in the past several years. I think studying for my ham license was my big step up because there were very good tutorial materials available to train me on the things which were a lot of hand waving until then. And of course it's not. It doesn't have to be that way. But it was nice to be able to do that without having to really understand Gauss's law. You don't need to know
yeah.
that in order to be able to understand some basic circuit theory and understand how resonance really works and how amplifiers really work and how antennas really work and all of this becomes demystified and then it all hangs together in a very fascinating and compelling way. You see
Oh,
all
it
these
does.
things.
And
Yeah,
well,
it's
when I
just
go through this
fantastic.
today, you'll see how it all the theory and the stuff that people say, oh, that's just theory. Well, guess what? When I measure real cable, it looks
Mhm.
exactly like the theory, and I've got the proof
What do
right
you
here.
know?
What do you
Yeah,
know?
well,
Yeah. So,
yeah. So
and I don't,
I'm gonna be so interested in finding out which properties matter for what. And I'm sure life's full of trade-offs. You got
mhm.
Peter to pay Paul. You find this compromise that sounds good, and this is what you've discovered works really well. I can't wait to hear an informed discussion around this because there's so much snake oil. Oh my
Oh my God,
God,
yeah.
it's just horrible. And so if you're really eager to learn, I don't know what you do. You end up on this one extreme of engineers
Well,
who are very dismissive of all of this and they understand the theory and they could explain it to you, but they don't even think it's worth their while. And then at
well,
the other extreme, just the
first, it's hard.
nuts.
Yeah, it's hard to explain this to a layman.
Yeah. Yeah.
Analog frequency range is especially complicated
Yeah.
because literally every single frequency is theoretically it's a different cable, which you'll see when I go through the presentation. Life is not all hunky dory on our cables at all. I don't
Yeah.
know who makes it.
Yeah, you have skin
And
effect is going to have it's frequency dependent and if yeah, I mean all there's a number of properties, but it's not like an infinite number of properties. It's like six or five.
uh, I mean, if you go first approximation, and
Yeah.
some of the tests will actually be like spaghetti sauce. It automatically
Okay.
lumps everything into the measurement,
All right.
including the things you may not know are important, but they are physically in there affecting the
Okay.
measurement
All right.
when we do these things. So, but
Yeah.
the problem with this is when people buy and look at hardware, they know an amp has an RMS characteristic, they know signal to noise ratio, they know slew rate. All these standard measurements exist. They could
Mhm.
exist for cable, but they don't. And that's always mystified me why cable is wide open. So what you want
Uh,
with in that environment is sales and marketing says, shoot the engineer, we're going to make up pros and make it sound wonderful.
make it up.
So
It's
they
awful.
talk, our car goes down the road like silk, and yet, well, why does it go down the road like silk? What kind of shocks are you using? What kind of
Right.
suspension?
Right.
They don't
Right.
explain anything. Yeah, they just assume that if they say it, it's true, and
Right.
they don't have any design idea to show what did you do in your cable that's making it different. What's your objective? And they have none that is demonstrated. And just saying what RLNC is isn't necessarily the objective. It's how did you get those values and why? What's the tertiary benefit of your RLNC?
Yeah.
Now, this
Well,
presentation,
let me, I'm sorry if I may interrupt you. I wanted to make sure I was clear on a couple of things before everybody shows up. So the first thing is the relationship of you and Belden and this the, well the company. I'm just a little unclear in the structure here.
oh, it's easy.
Yeah.
I worked for Belden for 35 years as a principal product engineer.
Okay.
Now, Belden always has what are called blue sky projects. Well, big surprise there. All engineering companies do that, which basically means take something we don't fully understand and run to ground and see how far you can get before the ability to move forward collapses. And I said, well, we haven't really looked at analog cables in a long time in terms of how could you theoretically make an analog cable better. they looked at me and said, well, that's probably pretty hard to do because that whole frequency range is kind of a mess. We get the basic cables, they're good enough, move on. And I'm like, well, let's see what we need to do to make them better. So basically, I had a blue sky project and I developed an XLR and RCA and a speaker cable to what's considered provable and better electrical parameters, what it took to do it. Not that you would sell the product via Belden per
Okay.
se, but as a knowledge base. We
Got
have a
it.
lot of things we have that we don't sell. For instance, at Belden, we don't sell everything we know
It's
about.
more on the R side rather than the D side. At that
Exactly. This
point.
is this is major research kind of a thing because none
Okay.
of this existed.
When was this roughly?
My last year of work, so roughly, God, it was like 3 years. So I'd say I retired in 2008. So it's about 2005 to 2008, somewhere in there, 3 year period.
Okay. Got it. So you did this research for Belden as a Belden employee,
Yes.
long time Belden employee at the very end of your career there. And
Well, yeah, because earlier on I didn't have enough GQ in my head to do it. I was too
oh,
dumb to
all right.
be.
Well, so this is in a way, the uh, the cap of this time, and anyway, you did this work, and then what happened? How did it get commercialized?
All right. What happened is I took the tables home and I auditioned them in my system. And the project was really designed to prove, as some of the pundits out there will comment, you can't hear that. So I
Mm-hmm.
was trying to prove no matter how good a cable really was, our existing products were good enough.
Okay.
What happened was it proved that our existing products, which were on my system, weren't nearly good enough. The
Oh,
cables made a notable improvement in the sound.
yeah.
Uh, Belden's like, that's interesting, but we can't go there. These cables are ridiculously expensive to make. That's not
Mhm.
our market, but it's
Right.
interesting that better electricals do appear to make a better performance in an actual application.
Yeah.
So I'll tell you what, my wife's been asking me to retire at 60 to be with her. She has an autoimmune disease that makes getting around more and more difficult as the years go by. She basically said, spend 5 more years with us or 5 more years with your buddies at work till 65. What's your choice? And I said, well, obviously, I'm going to take the 5 with you. So I told Belden, I'll tell you what, I'm going to retire. I'll take all of this stuff and I'll go to Blue Jeans Cable and I'll let them hire me and I will work with Blue Jeans and we'll market the cable through Blue Jeans to the direct consumer. And Belden will be the manufacturer of the bulk cable. And that's basically the
Oh,
relationship.
okay.
So it's not all that confusing, really.
Okay, so Belden is the manufacturer. It's where the research was done, but it's been commercialized with Blue Jeans Cable as
Right.
the marketing entity.
And I'm the Blue Jeans technical person. In other words, I work with the assembly of how
Okay.
the assemblies work, how the piece parts, bill of material, all that kind of stuff. So I pretty much
Right.
approve everything
You're
that's being done.
the chief engineer and product manager of
Yeah,
this thing.
basically. Yeah.
And then so there's production teams at Belden that put it together for you. That's fantastic. Now the other fellow we've been corresponding with, what is
Bob.
Bob? What is Bob's role?
Okay, Bob is the sales manager. So all the sales go through Bob to the plant because a
Got
lot
it.
of these cables are obviously custom. Customer says, well, I want this connector. I want it set up like this,
Yeah,
blah, blah,
yeah,
blah. So he makes sure everything the customer's ordering, if it's not a standard punch
right,
sheet cable, gets done. Now, a
right.
lot of orders go through on the web and he never sees them if they're just a standard order. But
Okay.
if someone has a special,
He handles the special orders, and he's the business brain in this company, Blue Jeans.
no, Kurt Denke is kind of the owner in business. Bob is
Okay.
more the Iconoclast sales manager, you could call it. So it's
Okay.
kind of like Chevy has Buick and Cadillac.
Okay.
Bob runs the Iconoclast part of Blue Jeans. So it's still Blue Jeans.
Oh, oh, that's interesting. So Blue Jeans is bigger than this cable
Oh
business.
yeah, yeah. Just like they sell more Chevys and Cadillacs, duh. I mean, the more
Right.
expensive products are more boutique,
Got
specially
it.
designed. And that's where I come in. Kurt's like, okay, we can handle the basic stuff, but this higher end stuff that's as complex as your cables are, we'd rather
Hmm.
have it be off to the side and create a website and keep it separate from the more general performance Blue Jeans products.
Okay. And will Bob be presenting as well, or just you
No,
two?
it'll just be me.
Okay, very good. Well, can I ask when you begin, if you could give this much of a thumbnail sketch of the company and structure, its relationship, and so on, to help establish context for everyone, because I think people will be coming in with different levels of background to know all this or not to know very much at all.
Oh, sure, it's no problem.
Thank you. Yeah, that level set's great. But I mean, it's sounds fair to say that there's some well, I had a friend in high school and college. We went to the same schools. His dad was a successful commercial artist, which is a tough thing to pull off because what happens for a lot of artists is if you become a fine artist, you can become very disappointed because it's tough to find patrons. And if you become a commercial artist, you feel a little bit like you're not really finding your destiny. That you're
Yeah.
you're you know you're doing your work. You're doing your day-to-day layout. You're designing things for clients. You're making people happy, but it's commercial work and it's a little formulaic for your taste. But you have to do what sells because you got to make a living. And then my friend's dad, occasionally he would have assignments where he could really be creative, and he did some award-winning work. And I remember him remarking how lucky he felt that he was in a position to be able to do the day-to-day, but also mix in some of this stuff where he could really push it. And your story reminds me a little bit of that guy. If by analogy you don't feel it's off base, I think it's a fair thing to say. Not everybody in engineering field gets a chance to uh, to do what you did to
No, they
put
don't.
this
I
together.
mean, and you're right. The standard Belden products are commercial grade products designed to
Yeah,
sell millions and millions of feet,
and they're really good.
and they're really good, but they don't go off the deep end, for instance, on, well, how good can an analog cable be? And oh, by the way, you have to prove it to us. And if you sell it, you can't go on anything except the data. In other words, you can't say our cable smells like roses smell or something. There is no marketing and sales. It's just hard engineering. And if people
Yeah.
don't accept the product with a certain level of expertise and measured qualities, well, we're not your company. It turns out, however, that the better I've made the cables electricals, the better it sounds. So that's kind of what brought it to market is, hey,
Okay.
making them better really did improve the sound quality. So early on, I went with Hanson in Cincinnati and Dayton and had several beta testers that all listened to the product. I
Hmm.
said, is this stuff, what do you think? And they're like, oh my God, this stuff is great for what you're charging. This is excellent. You guys have to offer this as a choice.
Yeah.
And then we had to decide, well, how are we going to sell it?
Yeah.
And I told Kurt, look, this is a data driven company, Belden. My
Yep.
suggestion is we drive it from a data driven approach and ignore what everybody else is doing. So that's why we can do what we're doing today. And our website is all data driven. It
Right.
drives some people nuts because if you tell them four things we know, they'll only want to know the fifth thing we don't. If you cover the fifth thing, then they'll want to know the sixth thing, if you know
Yeah.
what I'm saying. So,
Never satisfied.
it,
What are the price ranges for your Iconoclast products?
well, and it's a stickler. We wanted to keep the most expensive product below $3,000 for a
Mhm.
stereo 10-foot pair. We
Okay.
also made our standard lengths 10 feet on the speaker cables and 5 feet on interconnect. Why did I do that? Because in my system, those lengths are more appropriate for moves, adds, additions without having your cable
Yeah.
be too short.
I hate that when it's just a few inches. It drives me nuts. 3 feet
Well,
is not
yeah,
enough
and I
often.
found a meter length cable is too short. I found
Yeah.
8-foot speaker cables are just a little bit too short.
Yeah.
So our cables are a little longer than normal, 5 and 10 feet. But I found that for 99% of the people, that is way better off for them in terms of when they go to move something around.
Yeah. Yeah.
And two
I'm
feet of
I'm so
cable,
with you. Well, I think probably this 1 meter standard
it's
got
too short.
established when things were a little smaller.
Yep,
And
yep,
yeah,
absolutely.
yeah,
So
it's really a problem when the plug on one unit is way on the left and the thing it needs to connect to the plug is on the right.
yeah, Well,
Sadly
then
out of luck.
the other thing that interjects into it is how are the cables built? We have true air core products, and an air tube
Oh,
is not designed to be flexible. It's like a soda straw. You bend it
oh,
and it
okay.
hangs. So you have to give our cables a little bit of an arc to bend.
Yeah,
And
of
people
course.
demand that ultra high performance at a very good price. And the only way to do that is with true air tubes, but you have to
Okay.
pay attention to the bend radius. Uh,
Yeah,
Likewise, with the speaker cables, to get the LNC I'm after,
yeah.
the thing has to be compacted as hard as a rock, basically, because you really
No.
need to control the geometry. And
Huh.
that, of course, is going to affect how flexible they are. Now, is it a
Yeah, then you'll
problem
need
in
more
most?
length for sure. Yeah.
Yeah. Is it a problem in almost any system I've ever put them in? If you order the right lengths, absolutely not. If you order them too short, absolutely yes. It's
You
just that
will.
simple.
You'll be very unhappy.
Yeah.
Yeah.
So
Yeah,
Bob
that
kind of,
makes a difference.
yeah, Bob cruises the installation where people want to make cables exactly this length. And Bob's kind of like, no, we suggest that you measure it and add 2 feet at least, or else you're going to find that you're not real happy with the result. But so but yeah, the design also suggested a 10-foot, 5-foot minimum, suggested length. Now, if you have
Mhm.
mono amps, for instance, where the amp's right next to the speaker,
Yeah.
4 footers will work.
Yeah.
In
You
that
can have a
case.
different situation there, of course.
Yeah.
Yeah.
So
That's
we
always enviable. I for a little while I had some monoblocks under test in my system, and it was great. I love that arrangement.
yeah, I got my M40 sitting next to my CLXs or my T
Yeah.
plus A's. So
Yeah.
uh,
I,
I
I, I was I wasn't familiar with some of the things in your component list, so I looked them up and it's like, whoa. Well, if you can't hear the difference in speaker cables in that system, I don't know what you're gonna do.
Well, and I kind of had to get the speakers I did to evaluate these products correctly. So I
Yeah.
had the CLXs, which have probably the best mid-range of any speaker ever made, literally.
Yeah, they're
Then I
great.
have the CWTs, which is an electrostatic hybrid,
Okay.
which is, more like a speaker that probably most people will listen to, dynamic driver, kind of a thing. It's a line source, mind you, because I still like to listen to speakers that image incredibly well. And line sources, of course, are notoriously good at imaging.
Hmm.
Uh, so I ended up with that, and over the years, I upgraded the supporting components as well. And I found T plus A is a lot like Iconoclast, believe it or not. It punches well above its weight class for what you pay, but
Hmm.
it's still really, really well built. So I have a lot of respect for the T plus A products, and I've
Yeah.
been real happy with them.
Neat.
And got past labs, of course. I got my XP30, my
Yep.
XP25 still.
Yep.
Got my VPI Classic 2 with the JM Memorial tone arm and my Sumiko high output. So, kind of a mix of things,
Yeah. That's the way it
so,
should be.
but yeah,
Of
people say,
course.
well, what speaker should I get? And I'm like, well, I like both speakers for different reasons. I haven't found a speaker that's my CWT and my CLX in one speaker, at least not anything I can afford. So
I understood.
speakers
Well,
are interesting critters.
yeah, well, it's top of the hour. I want to welcome everyone to the meeting, and we can start to kick it off. Let me see. How many folks do we have online? Quite a few. This is really good. I'm going to
Now,
try
there's
to
probably
see
some that
everybody.
aren't. Is everybody sharing their images? I guess some are yes, some no.
It's a little difficult for me to judge here. Let me open up another window to see
Yeah,
participants.
we got one,
Okay,
two,
yeah.
three, four,
Yeah,
five,
we have
six.
12 people.
Mhm.
This is really good. Hope everybody is getting good audio quality. Yeah, I'm seeing a thumbs up. That's good. It's good. All right. Well, let's begin. Welcome, everyone. I'm Ken Schwartz, president of the Boston Audio Society. And yeah, today we have a very special guest, Galen. Galen, how do I pronounce your last name?
Is Gareis easy? Gareis and Gary, ice as an ice cube, Gareis.
Gareis. Okay. Well, welcome, Galen, and welcome everyone. As always, we'll begin our meeting with an open forum. So this is an opportunity for members to share observations and thoughts and ask questions of each other. That usually is about 20 minutes, 25 minutes, and then we'll begin with our feature presentation. All right. So with open forum, just speak up. I think you can just unmute
Ken,
your.
this is Ken Wax. I'd like to introduce a colleague of mine, David Hess. Dave Hess and I both work with the development of international standards for ISO and IEC. Uh, Dave's specialty is in cabling. And when I told him about the topic today, he was particularly excited and asked to attend. So here he is, and we're both looking forward to this presentation.
Okay, super. I think he'll be really happy with what he hears.
Yeah, welcome, Dave.
I'm happy already. Thank you so much.
Oh,
And
Thank
by the
you.
way,
Tuesday.
Dave, I don't know if Dave wants me to repeat it, but he shared with me that when he was in college, he sold audio equipment.
Yeah, I did too. 7 years at Good Vibe Sound across from Mackey Arena at Purdue. So did the same thing, lived on commission and was a service manager for several years at those stores. So it was fun. That was back in the old days when everybody had a stereo. That's kind of waned away right now, but I didn't know anybody that didn't have a reasonably nice stereo back in the day. That was the second thing you did, or maybe the first thing you did before you got a car.
Yeah, now they have earbuds and think that's a stereo.
Yeah, well, I don't know. Life moves on, so you have to accept it.
Some
All I
things
can
don't
say.
change.
Yeah.
All right. Well, there is the music too. Well, thank you. This is great. This is my what I guess my big hobby, I suppose. Anyway, what been involved for a long time and very interested in the whole discussion about cables. So happy to be.
Oh, we use your standards where I work every day, the ISO, IEC, and TIA, EIA standards. So I'm well aware of what you do.
Yeah,
Oh,
TIA is actually the organization that manages the U.S. delegation to
mhm.
ISO and IEC. The way it
Yeah,
works,
they're technically separate, but they are almost joined at the hip.
well, the way it works in the United States, every country has one vote, and the U.S. vote is submitted by ANSI, the American National Standards Institute.
Hmm.
ANSI are mainly administrators, so they authorize various trade associations, including the TIA, to do the technical work, and then we recommend how the ANSI should vote the United States position. And
Yep.
this is all voluntary, done by industry. Governments are not involved.
Well, we want to get it done right. So yeah, I don't think people realize how complicated.
Well, governments are involved in the ITU-T you may have heard of. The ITU does telecommunication standards for things like satellites, and that's run by the United Nations, and that is very governmental oriented. The State Department votes on that.
Yeah, that'll slow it down some, as far as the bureaucracy.
Well, the problem is that that involves a lot of countries around the world whose policies don't at all align with the US. So there's always conflict. In the work Dave Hess and I do in ISO and IEC, it's large companies, small companies, and eventually we come to a meeting of the mind because our goal is to promote world trade.
Oh yeah, absolutely.
Well, last year, they made me. I've been attending IEC since about 1990, and last year they made me the secretary of TC 46, and IEC TC 46 is RF and microwave um, copper cables and connectors and coax, and that's where the Category 5 standard lives.
Yeah, well, all the cat cables in general,
Where the
Cat
cat
5 on
cables
up
live.
to.
Dave is my go-to person for anything to do with copper cabling.
Mhm. He should know about them.
Well, very good. Thank you.
You're welcome. Now the questions aren't directed at me, you guys. They can be between you all. I'm just here. I'm not here to suck up all the attention right now until the presentation's officially started. So anybody bought
So I,
something?
I want to give an update on the saga of selling classical records. So I've been working on this collection of 4,000 discs that were a gift from a professor who had collected them over a lifetime. And he was moving and in a predicament. So I relieved of him his predicament years ago by accepting this collection. And I've enjoyed them for many years, but now I'm in the same predicament, moving to smaller quarters and having to find somebody to take them over. So I thought that I would sell this collection and then share the proceeds with the guy who gave it to me because he's still around. And wow, there's a lot of eager buying for my pop and rock records from the 1980s when I was in college. But classical records, didn't matter what kind they were, seems like they were radioactive. No one has been interested. So it's a shocking reality that there's just a very small handful of, I guess, older guys who, for whatever reason, are eager beavers to be collecting these things, interested in early pressings, unusual pressings. But musicians seem to be perfectly happy with streaming sources. They don't need the hassle of records. And people who are interested in records for records' sake want jazz and pop and rock. And they're not the slightest bit interested in classical. So if you are in this situation, that's what I found. And you may be lucky. We ended up finding some, what my mentor said, please find worthy recipients. So institutions were not interested, but I found some individuals who are basically have space and interests and musical tastes that align with this guy.
Yeah.
And they've taken it over. And there's been also a little bit of cherry picking from some other friends who said, "Oh, I want that. I want this," and came over and helped themselves. But that is the conclusion of this saga. And
Are
thank you
there
everybody for
still
your
used
help.
are there still used record stores in Cambridge?
There are in Cambridge. I think what you might be referring to, the one that was on Mass Ave. They've moved.
Right.
Yeah, they
Okay, well,
moved.
okay.
They bought in fact, it was that shop that bought my pop records. And there was some talk about maybe they would be interested in the classical, but at the end of the day, their customers are not interested in classical. So they end up with a lot of inventory they can't move and they get stuck. And
A
then
friend
there's,
of mine was forced to give away operas. He was settling an estate with a huge number of albums featuring full-length operas, and there was no interest.
yeah. So, if you're in this situation, it's good to be aware so you don't pull your hair out looking for dealers who would be excited to pick up your 30,000 LPs. Every dealer I talked to who could have conceivably been one of those, they all had the same sorry story of having just purchased somebody else's 20,000 LPs, and now what are they going to do? So yeah, your timing might be better than mine, but that's my little tale of woe. Um, anyway, turning it back over to,
I have an open forum item.
go ahead, David.
Well, first, the latest issue of the BAS speaker is being published, so that's done. That's volume 46, number 2. The other item is that I'm on YouTube Music, which you pay about $12 a month and get ad-free music, and I'm pleased with that. The sound quality varies all over the place, and so I was curious as to what is the limitation in sound quality? Is it YouTube or is it the provider of the content? So I decided to do some tests, and with the help of John Hajimian, I prepared some test tones and had him post them, and then I looked at the result. And the results were quite interesting and not what I expected. I'll write them up for the next issue of the BAS speaker. But basically, they do some level shifting. If you submit something at very high level, they'll drop the level. But that's not terribly significant. But the main question is, do they compress the audio that's been presented to them? In other words, compress the dynamic range. And so I put in a series of test tones, and I concluded, no, they do not compress the sound in any way, which is a surprise. The other test was, do they have a subsonic filter in the system? And the answer is no. It goes down to 10 hertz or below without any limitation. So I will write up something about that and present it to the BAS speaker. That's all.
So that means Google has the potential for being a high quality delivery mechanism.
This is not Google.
Well, Google owns YouTube.
Well, okay, YouTube. I posted a brief musical excerpt from Carmina Buranda, and it has extremely wide dynamic range. So that's not a limitation of YouTube.
Sort of accidentally discovered that they have a leveling function in their settings. And you tune into YouTube, you can go to settings and find, do you want to have it leveled by YouTube or not?
Right.
I chose not, and I found that the levels got higher for most programs, which I guess must be better. You just set your own level for each item that you tune in on, but hopefully it's better quality.
Yeah, I found that I put a series of tones, 0 dB, minus 10 dB, minus 20, minus 30, minus 40, 50. And it just shifted everything down 10 dB, which is kind of a surprise, but there was no compression.
Should I just jump in with a question? This is Nick Rodenhouse. It's about wire, but not cable. I'm a speaker builder, and I built a couple of sets of column speakers using 8 40-watt 4-inch drivers. They're the Dayton RS100 series drivers. And I always included in the previous column speakers a ribbon tweeter. Sounded great. I built the first set with Steve Luchan, and he loved it so much he ordered another pair for me. But I always thought these drivers will go up to 15,000 hertz and down to about 80 hertz. Why do we even need a tweeter? So I'm currently building another set of drivers or another set of column speakers. But what I want to do is put 5 of those little 40-watt drivers in series. If I do that, I can get roughly 7 ohms impedance with the finished product. But 5 of those drivers kind of makes me wonder if I'm going to try and run too much current through each driver when I turn up the volume on these speakers. Because 5 in series, you know, I guess I'm not enough of an electrician to know if I'm going to toast coils when I put that many little drivers in series. Does anybody have any sense for that?
You should see just the opposite of what you said. If they're in series, it's going to be, you're going to be increasing the resistance in that circuit, which is going to decrease the current going through each driver. All right, so the current's going to be the same going through every single driver, but the I equals E over R, you're increasing R by putting those drivers in series. So R gets bigger, so the current through each driver gets smaller. So the power handling should actually go up, not down.
Super.
Okay. Now you still are going to have to level match them. Of course, a tweeter with 1 watt going through it will run you out of the room. I have some data that today that will actually show some of what's going on there.
Yeah, it's
so you might be interested
all
in
10
this.
drivers are identical. All right, so it's we don't have to worry about matching sensitivities or anything like that. 10
Well,
identical.
you're just using the one set altogether. Is what
Well,
you're running full range.
Full range.
Okay, there
exactly.
you go. Yeah, you won't have to. Then there's nothing else to level match to. Okay, I got you. Yeah.
Yeah.
I have a chart that's kind of interesting that will be of interest to you as far as what actually goes on when we listen to music in our speakers. It's not what people think in terms of where the power is actually going and how much. I work with Paul McGowan at PS Audio, and we kind of did a little thing on it. So you'll see that today.
Great.
Any other questions or things you'd like to share in the open forum? All right, well, if not, then let's move on to our feature. So thank you, Galen, for joining us today and presenting about the work that you've done with Belden and Iconoclast on these high-end interconnects and speaker cables. I've asked you to give us a thumbnail sketch about your career and background, and I know you'll kick it off with that. But let me just say that I'm reminded of a friend's dad when I was in high school and later in college. This friend's dad was a very successful commercial artist in New York, doing advertising design for companies like McDonald's and American Express, and was a celebrated, successful guy. And I remember him remarking how lucky he felt because most commercial artists aren't really able to do the kind of creative work that they like to be able to do. They're doing day-to-day layout and design, advertising, planning, and things like this, but it's not super satisfying. And he was really pleased because he was, just by luck of the draw, was able to do some work that pushed the boundaries as far as he was concerned. And so he infused art and science together and his craft. Anyway, I bring this up because I think it's a good analogy. When I was chatting with Galen, reminded me of his story, because here's somebody who, I think, is it fair to say, in an unlikely place in Belden Cable, was able to really stretch the state of the art in terms of a high-end offering into the nosebleed category. So it's really an interesting story about melding the art and science into a new product. So with that, let me turn it over to you, Galen. If you could start us off with an explanation of the company and the history that led to this, and then we'd be very eager to see your presentation.
Okay, yeah, there's a lot of conspiracy theories going on at Expona about Belden and blue jeans and what it all means. But it's pretty simple. I worked there for 35 years, worked my way up to principal product engineer with them. And toward the end of my career, they have generally, you can really do a blue screen, blue sky project anytime you want. But I had enough critical mass to actually look at analog cable after working with digital and everything else over the years to actually figure out how to make these things actually better. Belden's general feeling was, okay, this is for information only, and it will put the technical expertise to work in unknown areas, but we're probably not going to sell cables that are extremely high end on the analog side because that's just not our market. It's too small. But they let me take off with the project. So over a period of 3 years, I developed RCA XLR and speaker cables that were, well, extraordinarily good when I tested them on my system. I had beta testers and people listen to these products and said, wow, I didn't realize if you really truly did make our LNC measurably better, that it would actually work. In other words, you can hear that. You hear a lot of people say, well, I'm interested in relying on cable, but if I can't hear it, what's the point? Well, that's exactly right. But a lot of people can hear it depending on the level of your system. So I went to Belden and said, I tell you what, I worked my butt off. I'm going to retire 5 years early to be with my wife a little bit. But I'd like to work with Blue Jeans as their product engineer on the Iconoclast line and market the product through Blue Jeans, since Belden generally would be better fit to make the bulk cable to my specifications and following my patents. Belden said, yeah, that will work. You'll just be a customer of ours. You'll work for Blue Jeans, and they will take their bulk cable and manufacture it into assemblies to my specifications, and then we'll market them from Blue Jeans. So that's really the relationship. All right, without all the conspiracy theories. So it's pretty straightforward. I worked there, retired, worked for Blue Jeans. Belden makes the bulk. Blue Jeans makes the assemblies, and we're a data-driven company. So you'll notice on our website and this presentation that we have no flowery sales or marketing acronyms at all. As a matter of fact, we don't even have sales and marketing at Blue Jeans. We have me. We have the sales manager, mind you, who makes sure your order gets put through right. But we do not have undefinable attributes associated with any of our cables. So you pretty much have to look at the electrical, see if you agree with it, look at the white papers. You have a 30-day free policy to listen to them. And that's generally how we chose to go to market, which I know is radically different than any other cable company. And for the life of me, I don't know why. I think we should be the way it's done, not the way that it isn't, but well, that's neither here nor there. It's how we chose to do it. So that's kind of how the product line came to be. Is the beta testers said this stuff is far too good to not sell. And I said, well, it won't get sold if Belden has to do the sales and marketing of it. It's beyond their ability to want to even latch onto it as far as their sales and marketing, where they're driven. So it went to Blue Jeans, a much smaller company that can basically manage this the way it should be managed, a kind of more of a smaller and more personal level on these technical products. So that's kind of where we are as far as that relationship goes. So here we go. All right. So jumping into the presentation, if there's anybody have any questions about the relationship between Belden and Blue Jeans and Iconoclast?
You say BAV product line. What does BAV stand for?
Okay, BAV is our Belden audio video. We have 3 lines of products. Basically, it's kind of like Chevy, Buick, and Cadillac. The BAV line take a lot of what we learned building Iconoclast, but figured out how to make them at a much more affordable price point. So people sort of have a middle jump in the product range. They want something a little better, but they maybe don't have $15,000 speakers. They don't need to go all the way up the ladder. So we developed what's called the BAV product line, which actually is an overachiever as far as the product performance and measurements. Is actually very, very good. So that's a Belden audio video, and then you have the Iconoclast, the top, and then of course we have the standard Belden products sold through Blue Jeans, which are the standard Belden offerings that we've
So
had.
your 35 years was at Belden.
Yeah.
Were you involved with analog cables for your career?
No, I was involved with everything for my career: fiber optics, analog, data cables, coax, you name it, did everything. So at the end of my career, I was primarily high frequency digital Ethernet communications cable. So that's what I retired. But early on, at Belden, they don't want you to get too complacent. So they move you on purpose to where they think you're going to fail. So you learn something. So you're moved about every 5 years in terms of your product mix. Because they realize to be good at digital, you have to know something about analog and vice versa. And that's one of the reasons why I could develop these products, is I did so much work with digital that it made me realize some of the things could be transferred over to analog and improve the state of how these cables actually measure and how they work. A lot of these slides you'll see I was involved in actually developing 25 years ago when we worked with some principles of analog circuitry and the problems that it presents. And that, of course, is brought to the forefront when I developed the Iconoclast products as far as what you see today.
I worked in the test equipment industry many years ago, and the biggest challenge was to find engineers who understood analog. And
Oh,
that
yeah.
was 30 years ago. It was getting difficult.
Well, and there's not a lot of people that want to work with analog cables, because once they start to get into it a little bit, they realize that it's incredibly complex. And it's not going to bend to your will. And it's due to the physics of how that analog frequency range works. And again, we're going to cover all that today. Some of you will leave pissed off about it, but it's not as good as you think it is, even if you try to optimize it. But it's what the physics are and how these things really work. I don't care what name you put on the cable. If you fire the engineering department, replace it with fancy pros on your internet site, the physics is the physics, and that's what you have to work with on these products. So any other questions? Okay, so let's get started. All right, and we're going to kind of jump back and forth a little bit between digital and analog, because we sort of have to in order to give you a well-rounded picture of actually what's going on. This first slide actually is an RF slide, and it's a simple tank circuit. And a lot
Your slides are not advancing.
Yeah, so Galen, the way you've presented the slides lets us scroll through them.
Okay.
And I think it might be better for certainly the recording if you're able to present them one at a time and direct us at the slide that you want us to see. Do you know how to
Okay,
do
so you're not seeing, what are you seeing on your screen right now?
So I'm seeing all of the slides available.
All of the slides?
Yeah, and I can scroll
I'm only
through.
seeing the first slide.
And it must be a setting in your,
No, what you should do is run your PowerPoint and share the screen that has that.
Yeah, I think that would be a good strategy, Galen, if you could.
Okay, man, it's not supposed to do that.
Yeah. Well, it wouldn't be Zoom if it didn't behave in a surprising way.
Okay, let's try something here.
So you stop sharing, you pick the window you want us to see, and then share it.
Okay. I click share
No, first click stop sharing
on the Zoom.
on the Zoom.
Okay, I'm seeing share, but I do not see where it says stop sharing.
I-
I'm pretty sure it must be down at the bottom. Here we go.
No, it didn't stop yet.
Okay, it's not, I don't see where it's telling me to stop sharing.
I should be somewhere right on the screen you're looking at near the top.
There we go. So you've just started your screen sharing, and we're seeing now your Zoom.
Yeah, you picked the wrong window. You got to stop sharing, you got to start PowerPoint, and then pick that window. No, don't. You stop sharing. You're showing us everything on your desktop. We don't want to see your desktop.
Ken, it may be that he's got his presentation in
Well, the presentations is a, right now the presentation say
the PDF, isn't
PDF.
it? Yeah, so go ahead and open up the PDF and you just walk us through the PDF as you want us to see it. There you go. I just want you to direct us through the document.
Yeah.
Scrolling.
Now everybody sees just the one screen now, right?
No, can you go to full screen?
Yeah. That's great.
No, not just blow it up. Go to like Control L, I think is the, yeah, that's it. That's better.
Okay, that should, this I can't ever get rid of.
Yeah, I think we're in good shape here. Let's let you go
Let's
ahead.
go here. Now this looks like it's working.
You'd make it as big as possible. That would be great.
Yeah, if
I think
that
that's
might work. We can size it based
Thank
on the
you very
slide if something is not visible. Okay, so are we set, we think?
Yeah.
Cool, all right. Yeah, I've only done this once before and it seemed to work well in Zoom if I imported it into Zoom, but oh well, I guess it doesn't all the time. Okay, so this first slide again is RF. And RF actually is a reasonably simple environment to work in, all right, because your velocity to propagation, your capacitance and inductance are all constant. And that's the definition of RF resonance, is when all those variables reach a steady state. And we'll look at some measurements that exhibit that. But basically on your tank circuit, if you increase the frequency to where the lowest frequency that has an equal voltage on the inductor and the capacitance, but opposite phase, means that's the beginning of what's considered resonance. Any frequency above that will maintain resonance. Now, a lot of people will look at RF and they'll come down here and say, well, gee, I know the impedance of RF. It's easy. It's square root of L over C. What you need to understand is, why is it L over C? What happened to phase? Inductor has a phase property. Capacitors have a phase property, but they're equal and opposite, so they cancel. So you wind up with just a root L over C. Now, that's not what happens in our analog frequency range, though. We have phase and on the inductor and capacitor all the time, and it changes at every single frequency. So when you think these audio cables are relatively simple, they're actually incredibly complicated, because every single frequency really is behaving differently going down our analog cables. That's not true at RF, because again, the L and the C and the R create a resonance frequency to where your capacitance, inductance, all of that stuff is constant. So that makes life a heck of a lot easier to design cable. Now, when you look at a lot of cables, what you'll realize, what people aren't telling you is if you look at a 75 ohm cable, actually a 77 ohm cable gives you an optimal attenuation factor. Due to the constraints of how the connectors are made over the years and a long history of just engineering compromises, we ended up with 75 ohm cables. Likewise, with a 50 ohm standard, it's kind of off from peak power handling of 30 ohms. And again, this is at RF only. So even though we have 75 ohm cables and 50 ohm cables, they're really slightly off of the maximum attenuation factor cables being 77 ohms, and the power handling really is best at 30. Part of the problem with the power handling cables is they didn't have dielectrics way back in the day that could allow a cable to handle a lot of power. So they basically made the cables 50 ohms to compensate for that. So we see a lot of compromises depending on when these standards are derived. But if you really were making a custom cable for maximum power handling, you make it 30 ohms. And if you wanted the lowest possible attenuation, you make it 77. There are 150 ohm twin axial cables, which is like 275 ohm cables in parallel. All right, for instance, that also try to achieve low attenuation, but they're still not quite on that 77 ohm standard. So again, we do have some trade-offs in modern cable at RF. This does not affect analog. These are just some background information on how RF kind of behaves. Now, if we look at our frequency range, things get very complicated. Down here in the lower right, we see our ZO equals L over C. That's basically where everything reaches resonance. That's a super simple curve. Everybody knows it for the most part that looks at cable much. But we have a transition zone as the frequency drops that gets massively more complex to fit what actually happens in here as we go from low frequencies to middle frequencies. And then finally, we get to our analog frequency range, which still has a reasonably complex curve to handle our super low frequency ranges. So as we go down in frequency, all of these factors start to enter in. In other words, they don't go to 1 or 0. You know, the old professor in high school, whatever, college would always say, oh, see this term, it goes to infinity, so we can pretend that it's just not there or it goes to 1 or 0. A lot of these things factor out, so all you're left with is L over C. Everything else goes away. So that's not true when you look at the overall picture of everything at once. So this is where we live today, right here. Okay, this is actually 100 kilohertz. So this is kind of what is impacting our hobby, is this guy right there. Now, if you take standard cables, any cable, I don't care how fancy you want to make
Galen,
it.
I'm
Yeah.
sorry, could I ask a question in the previous slide?
Mhm.
Why does the L term disappear for the lower frequencies? Wouldn't it have a contribution in some degree?
No, as you go down in frequency, inductance requires current. And when you're looking at these high frequency cables, they generally are into high impedance input, so there's not a lot of current in them. So the L tends to go away. C goes up significantly as you go down in frequency. We'll also see the data that shows that your cable looks like a capacitor basically as you go down in frequency. And inductance goes away. As you go higher and higher in frequency, the capacitor looks like a short, and then the inductance starts to enter in. So to a first approximation, the L goes away. It becomes so small. So they're equal and opposites, basically, believe it or not. They tend to want to do, if one thing's going up, you know, if you know what C's doing, you know L's doing the opposite, in other words. And we have some data that will also show that in terms of what happens with L and C.
Is this independent on the type of cable, whether it's twisted pair, whether it's shielded or not?
No, this should be for any type of, you know, cable that's driven into its quote resonant frequency. Now, the problem with analog is what's the resonant frequency? And we'll talk about that a little bit today. It doesn't have one. All right. And the wavelengths are too long to put 10 wavelengths or so into a cable to develop what's called resonance. We have to use a special measurement technique on low frequency cables called open short measurement, because we can't use formulas based on the data to easily derive what's going on at the low frequency range. It's just too complex. So to make sure I'm getting numbers that are meaningful, we measure our cable in 10-foot lengths using open short, because that's what the cable's really doing. And that's kind of like spaghetti sauce. All the factors that enter into what the cable impedance really looks like are in there. And it does correspond with the theory in terms of what the data is doing as far as whether it's getting bigger or smaller, staying the same. So again, analog, you about have to measure it. You really can't, if you really want to tell someone what's really going on, you just can't throw a formula out there and plug in numbers and be as close as you'd like to be. So there's too many variables at every frequency going on. So to answer your question, I guess the answer really is no. It depends on the cable and it depends on the frequency. But it's generally going to follow this format. Okay. So now when we start looking at the measurements, we'll notice that this is 1 kilohertz all the way up to a megahertz. And you notice that the values, once they're set, they stay pretty close to the same. All right. No matter, some cables are actually completely dead flat. Now these are shielded, so you have an outer pair and an inner pair. So the outer pair is closer to the shield, so the capacitance is higher. The inner pairs are further away from the shield, so the capacitance is lower. So they generally follow the general rule that the closer you are to a ground plane, the higher the capacitance in the cable. Some single cables that are just single pair cable, you'll notice the capacitance is about as straight a line as you can get. Now, when we come down here and look at inductance, first thing you're going to notice is, well, gee, it changes. I thought you said it was stable. Well, it's pretty stable. You go 0.3, 0.2. These are very low inductance values for the most part. What do you suppose is doing this right here? What's causing that transition? Well, if you know what makes an inductor, it's the distance two conductors are from one another. As these conductors are going up and up and up in frequency, the skin effect pulls the current from the center of the wire to the outside surface of the wire. When it does that, the majority of the current is on the surface of the wire, and therefore the inductor becomes lower in value because, of course, the current carrying part of the wires are on average closer together. When you go down in frequency, down here, we have what's called diffusion coupling. The current through the wire shares the entire cross section of the wire. So the wire appears as though it's further apart based on the current density distribution. Here, the current density distribution becomes closer, so our inductance will take a dip. And it does it for pretty much almost all conductors, depending on what frequency you go to. So that's going to be a common issue right there. This isn't really a problem at RF because if you notice, it occurs right at the RF frequency range. So they're pretty flat in the RF range, yet you do have a different set of values when you work with the analog range. So when you say the inductance is pretty much constant at RF, that's true. It's constant at analog, but it's not constant throughout the whole frequency range. So you sort of have to understand this little skin effect jog in the curve. All right. Your capacitance is so close to the same that when you calculate the capacitance of a coax cable, you actually measure it, believe it or not, at 1 kilohertz. That's the industry standard, is we set up the unit measured at 1 kilohertz. And when you use your frequency calculations for coax or twinax or even a Ethernet cable, you take the value measurement at 1 kilohertz. You can't do that with capacitance or inductance because of this change that we see due to the skin effect. Any questions on this slide? Were people aware of what actually happens here when you're working with these cables? A lot of people aren't aware of what inductance is doing and why, but it has to do with the skin effect. And also, if you have a super high current cable, it has to do with what's called the proximity effect. If you put a lot of current down two wires close together, that will also pull the current to the inside surface of the wire along with skin effect. So the two attributes are superimposed on top of one another. If you flip the currents around, believe it or not, it will push the current to the opposite side of the wire to add confusion to the mix. So you have the inductance and skin effect trying to pull the wire current to one side, but you have the proximity effect trying to push it to the other side of the wire. So you can also get unpredictable inductance values at high current RF cables. These are not high current RF cables. These generally are what we consider signal level cables, 1 volt peak to peak. So we don't have to worry about proximity effect too much on our analog cables.
So Galen, I have a question. If we confine our concerns with the, audible frequencies from say 20 to 20,000 hertz, that would
right in here.
This left part. So those graphs look, at least for the inductance values, very flat, and even the capacitance values in terms of picofarads, we're talking a couple picofarads difference between the very lowest frequencies and the highest frequencies. Is this the source of the difficulty, or are these things that you would consider negligible?
These would generally be negligible in terms of the variation. You need to know the root values, of course, but when you sweep the electricals, it automatically takes into account this change in capacitance when you do what's called a swept test. So a swept test is, like I said, it's more of a spaghetti sauce measurement. It's measuring everything we fundamentally know, including any tertiary elements that you may not know are actually in there impacting it. For instance, the proximity effect. There is proximity effect even in low current cables. It's just so small that, well, you don't bother measuring it. But is it there? Yeah, it's there to some level. So if you measure inductance out here, you definitely are measuring the proximity effect and the skin effect. You can't tell one variable, I'm not interested in, you go away. It's just going to slowly reduce in magnitude based on the physics, but it's never going to completely disappear until you get to DC. That's just simple AC circuit theory there. So it's always there to haunt you, whether you think you're being scared by it or not.
So did you tell us what kind of cable that you were measuring there? Is that just single strand? Is that a multi-stranded? How many strands? How compacted are the strands? What is the cable that you're testing here?
Okay, these are the Belden part numbers, all right, and these are coaxial cables, and this is a multi-pair, all right, multi-conductor cable. So this is a multiplicity of twisted pairs underneath the shield, and these are basically single pair and coaxial cables. That's why the capacitance is a dead straight line, because the distance to the shield is not crowded by the geometry like it is in 9515. So you have outer layer of pairs and you have an inner layer of pairs, all right, on these products. So the closer you are to the shield, it's going to make the capacitance go up, and the inner pairs are towards the middle of the cable. The capacitance is naturally going to ride lower. All right, is what these are. These are generally, though, meant to demonstrate what happens in real cable. Any cable will do this. I don't care who makes it, what it is, you know, the fancy marketing terms, names are immaterial. I can measure any cable and you're going to see this same general set of curves. Now, depending on the design of the cable, its general values over here are going to be slightly different, but you're still going to get a reasonably straight line across frequency. That's the point I want to make, is that your capacitance across the entire frequency range is constant. A lot of people don't realize that. Inductance, likewise, the capacitance or inductance across the frequency range that you're using is constant in RF for the most part, and then your frequency range in analog is roughly constant. But you can't swap the two, because there is enough of a dip here that if you're trying to make a 100 ohm cable dead nuts, all right, for instance, and you have square root of L over C, your L is going to be here and it's not going to be over here, so you're going to miss your target impedance. So you do have to be aware of what the inductance actually is at RF when you're working with this. Capacitance, not so much. Okay. Now there are some simple equations at RF that work. You can take 101,670, a constant, divided by the capacitance times the velocity of propagation. Your velocity of propagation in a coax is pretty simple. It's just 1 divided by the square root of E, which is the dielectric constant. So if you have a conductor with a plastic around it, a shield, you're going to have a very simple transmission line, and this 101,670 works about every time. So if you take 9269, all right, for instance, and you basically take the square root of L over C, and this is in farads, by the way, and henries. You got to use the right units. So if I use my, you got to give to the -8 -12th in here and calculate, you're going to get a 92.7 ohm calculation. If I go to the simple formula of 101,670 divided by capacitance times velocity, you're going to pick off your capacitance times velocity, and it's going to show about an 89.6 ohm cable. Not exactly the same. All right, so again, there are some small approximations that are made using these two different equations that will get you close, but the only way to determine what the cable really is without any approximations, i.e. everything that's really involved and not dropping a term out here or there that you think is not significant, you really have to measure the cable's L and C at the frequency of interest to know exactly what it's really doing. Now, again, I use what's called the open short method in analog. All right, and we'll cover the open short method, all right, in detail a little bit later on in the presentation. But the open short method is a manual method that measures each individual frequency in order to derive what our analog cables are really doing. And it is important to measure the length of cable that you're actually going to be using, or very close to it. You wouldn't want to measure a 10-foot piece of cable and then have a guy say, well, I'm using it when it's 100 feet long, because the open short impedance of analog cables is in a state of flux. As the cable gets longer, the values keep changing, believe it or not. So you do want to measure a cable length close to what we're actually going to use it at. So when you see my cables measured, they're usually going to be measured at 10 feet or 5 feet, because that's the length the cable's actually done going to be when you build an assembly for a system. So again, I can't use these. This does not matter how long my cable is. They're always going to give you roughly the same answer. This is length dependent. All right, so you're going to see a change as the cable tries to look like a transmission line if you made the cable hundreds and hundreds of feet long. Never can do it because our wavelengths are too long. So we don't really have resonance in analog cable. We do have an impedance per se, but you can't classify it as the same type of reactive impedance that you would see at RF, where the L and C are in resonance and the phase is gone. We have phase in our analog measurement, which will also be shown. And there's some interesting things about that that I think that people aren't really aware of. And there's also some misinformation out there to make marketing sound better than it is on these cables. And I'll tell you why that is. Now, here's the slide that everybody understands, but they don't know they understand it. If I take a cable that's DC, direct current, and I put a signal down it, what's the velocity of propagation of direct current? How fast does a signal, quote, travel at DC after you throw the switch and you get through the transient and you're looking at 5 volts on your oscilloscope? What's the velocity? It's 0, isn't it? It's nothing. There is no velocity of propagation at DC. Mother Nature is kind of smart. She doesn't go from a relatively high velocity cable at RF and instantly all of a sudden wind up at 0 at some magic frequency. She doesn't come straight across, hit DC, and go straight down. She doesn't do that. What she does is she said, okay, as my frequencies are dropping in frequency, my velocity of propagation is slowly going to intersect 0, DC. This is 20 hertz. This is 1 kilohertz here. And 20 hertz is down here, it's single digit, it's below 10%. So the velocity of propagation of a signal going down a cable can be as much as 67 or 70% slower in the base frequencies as it is at the treble frequencies, even, all right, in a, analog cable right here. So you're looking at values in the 60% range, and you're looking at values down here at 20 hertz that are single digit. So you can easily see there's a 45, 50% difference in the velocity of propagation. You can calculate this, get rid of that, and you can manipulate it with this particular formula that is only good over a range of R and C. In other words, this is called a fitted equation. It's designed to match what the delay, you can measure delay, which is the amount of time it takes a signal to go from one end of the cable to the other, and you can convert that to a velocity. But this equation is designed to work on cables that are within a range of R and C. So if R or C gets really big or really small, this equation won't be quite as accurate, but it still shows the general characteristics of what these various different kinds of cables are doing. Notice this curve looks noticeably different. That's because this is a different conductor material. These are all copper. So you notice Mother Nature said, well, if I use copper, my velocity curves are very similar. They just go up or down depending on the design of the cable. If I change materials, however, I see a different knee in the curve. So things start to become a little different if I use a copper covered steel versus the 3 copper conductors. But if you want to make an analog cable more accurate, you need to try to basically get rid of this non-coherence that's existing in an analog cable. So to do that, you need to start working with R and C. You need to make R smaller or C bigger. You really want to do the bulk of your lifting by increasing the value of the resistance of the cable, however. All right. So that's where you're going to do your, do the bulk of your concentration. Now, our friend is right here. The speed of light in a vacuum is 310 e to the 8th. So people will say, well, thank goodness that the speed of a relatively short length of cable, if I look at it in terms of nanoseconds or picoseconds, even though we have an 80% difference, at least it's an 80% difference of a small number. All right, that's the general feeling. All right, and that's a reality. So this actually is why our stuff tends to work as well as it does, even though we can significantly improve it if we want to, and put it on our systems and see what that does. So one of the things that I've done is I've looked at this data, that this is some of the data I measured like, geez, 35 years ago. All right, this slide and this slide, this is all done years and years ago, and it was just kind of floating around in the back of my head what to do with it. So again, we can adjust VP based on what we do. Now, omega is 2 pi f. We see sometimes we'll put 2 pi f in the equation, sometimes we'll put in omega. Engineers generally like to abbreviate stuff amongst us. That way we can keep everything secret and confusing. But omega just means 2 pi f. That's where the frequency comes in. So this is a VP is a frequency dependent variable through the analog frequency range. So in other words, our analog cables are anything but coherent. They're absolutely not coherent at all. Now, if you manipulate R and C, this is one cable with a 24 gauge conductor. This is another cable with a 28 gauge conductor, 020, 12 roughly you can see a significant drop even through the analog frequency range, which is kind of right in here. All right, even as low as 1,000 hertz, you start to see a difference in the arrival time between these two optimized products. A standard cable would even be above this particular product line. So this would be like the Series 1 Iconoclast. This is the Series 2 Iconoclast with the 28 gauge. All right, but when you notice this is 10 hertz, this is 20 hertz, you notice this is almost a single digit velocity of propagation. Now, the interesting thing about this curve is someone that's in the know, some of you cable guys, I know there's one out there, he already introduced himself. Look at my velocity of propagation at RF. It's 50%. What's the velocity of propagation of Teflon? You take 1 divided by square root of E. The dielectric constant of Teflon is 2.3. So you should see 69% up here, but we don't. Why? Because this isn't a coax cable. This isn't a conductor with a dielectric around it and a shield. That 1 divided by square root of E only works in a pristine transmission line environment. It does not work in a heavily woven complex design used for analog frequency range. We don't care about RF. If this were an RF cable, this would be a colossal failure. If this is an analog cable, it's a success, because the lower I can pull this velocity down, the flatter this curve becomes and the more coherent our signal transmission line becomes. You do that by increasing the value of R. All right, that'll pull down our VP. Now, how you increase the value of R is you have to use a multiplicity of smaller, higher resistant wires. A lot of people are real big on skin depth in analog cables, especially in our hobby. It's sort of misplaced, because the real reason you want to make R high is to improve the velocity of propagation coherence. You don't really care about skin depth, but guess what? When I make R smaller to improve my coherence, it automatically makes the skin depth or wire efficiency better, because my wire is getting smaller and the signal's transferring itself through the larger cross section of the wire, the smaller the wire becomes. It's not all just sitting out on the surface of the wire, which of course is, in our terms at Belden, is just increasing the wire efficiency. So a 28 gauge is quite a bit more efficient than a 24 gauge high frequencies, because it's using more of the wire. You're not wasting material inside the wire. So when I try to improve coherence, I automatically do it, or improve skin depth. When I chase coherence, I automatically improve skin depth. So you get one with the other. A lot of people think you're chasing skin depth. That's not true. I don't care about skin depth, believe it or not. It wasn't my reasoning to use the smaller wires. A lot of people think it was. Had nothing to do with that. But I get it for free, okay? So for those that are worried about skin depth, you get it. But the real reason to do it is not skin depth. It's improving the coherence through the analog frequency range. And the design of the cable helps pull this down from 70% roughly down to 50. All right, so that again flattens this curve. You'd really like to see this curve be a straight line somewhere, but Mother Nature's not going to let us do that. Mother Nature likes these Gaussian, hysteresis type curves. And we're going to see a backwards hysteresis curve of this a little later on in the presentation to further cement the fact that Mother Nature, she likes to do things gradually. She's not into major changes in a big hurry.
Hey, so Galen, a question for you. If you go the previous slide. So I understand the y-axis in this graph is percent of VP, which is that the velocity of light?
Correct. This is like 60% of the velocity of light in a
Right.
vacuum. 100%.
Okay. So then, if we're looking at the audio frequencies, which would
And
be
this is 10. This is
yeah, so
right here. That's
okay, so
10,000.
just for
So
simplicity.
20K is about here.
Yeah. Okay.
So you
it's
see a pretty good difference through the analog.
anything from 0.2 down to almost, well, infinitesimal. It's really, really tiny percent of the velocity of light. Now, my question for you is, how does that translate to differences in latency in, let's say, nanoseconds? Are we
Okay.
talking, can you translate that to take the top of the frequency range that might be audible, let's say 10,000 hertz, and compare it with 100 hertz, which is, very much part of a musical program. So there you go from the normal tones all the way up to the highest frequencies. What sorts of latency concerns are we talking about here? Are they measured in microseconds even?
Well, the thing that is making the difference really is the harmonics off the fundamental are no longer lined up right.
Exactly. So can you just characterize that in seconds terms? Is it
Oh, it's going to be in the
milliseconds or is
no,
it
it's in
milliseconds?
the no, hell no, it's in the picoseconds, literally. It's actually amazingly small that you can hear
Oh.
the differences these changes
You
make.
can hear the difference in picoseconds, you're saying.
Okay, well, you can certainly hear that along with the other changes in the cable. I'm not saying this is the only thing in the cable
Okay.
that's making. This is one of the things I wanted to manage in the cable. There's some other things in there that also will determine what the cable sounds like as well. This is just one of the attributes that you're
Right.
after. So again, analog cable is very strange. You can't, it's all superimposed one thing on top of another. RF cables don't have that problem. Everything tends to be a one-shot pony, and
Yeah.
how they behave. Analog, every single cable, every one of these points, this is technically a different cable at every frequency. Now, if you look at this equation, 3 times 10, you just take that and multiply that by 40% or 60%, and that's your meters per second difference. You can calculate that quite. That's why I put this here. All right, I don't like to deceive people in terms of the fact that this is our buddy. This is actually what helps our cable work better than we would actually expect them to, considering we got curves that don't look so great. This actually looks pretty bad. If you're saying, if you just go to absolute terms, this wire is not coherent. You have a 40-50% difference in arrival times on the low versus high frequencies. And there's no way, by the way, to get rid of this. All cable are subject to this. Now, the level at which you can compensate for it depends on the design of the cable and how much you want to pay attention to. Are you trying to do it, or did it just happen by accident? I did it on purpose. I knew exactly what I was doing when I designed these. So again, this is kind of what I want to talk about with as far as the coherence and what actually is going on with analog. And that's why, again, it's just as simple as DC has no velocity, and RF is going to be the limiting velocity of the dielectric that you chose and the design of the cable. All right, so it's going to go here and it's going to go there. I don't care whose cable you buy, what marketing or sales says, you're going to get a curve that looks just like this. It's going to be somewhere in here, one way, shape, or another, but it's going to form this hysteresis type of curve. Now, this is not new information. This chart really, I plucked this off of early Belden stuff from, I think, 1910 or 11, somewhere in there. These are theoretical calculations that show what happens to the impedance as the frequency goes down. Well, when the velocity of propagation goes down, remember our equation was 101,670 divided by inductance divided by capacitance, L over C. Well, as the velocity goes down, the impedance has to go up. It actually goes up to infinity. Well, why would the impedance go up to infinity as the frequency drops? Well, DC by nature has basically an infinite ability to prevent AC current to flow, or else it wouldn't be DC, right? So if you look at it from a super simplistic viewpoint, yes, of course, DC blocks AC, so the impedance must be infinity. That's our, quote, classical definition. Of course, if you look at impedance as a resistance, all right, to frequency flow, DC is infinity. And of course, as you go down in frequency, the resistance to AC current flow gets worse and worse and worse till it basically stops it altogether at DC. You don't have any AC. So this is why this curve calculates this way. And these are done in theory, by the way. That's why this is so perfect. Now, this is the curve that also is interesting. This is our phase angle that our cable sees. At RF, the inductance and capacitance have equal and opposite phases, even though, and the voltages are identical. That's why it's called resonance. So we don't get any phase. It's basically zero in theory. As we go down in frequency, our cable looks like a capacitor. Our inductance drops away predominantly, and our capacitance takes over. And this is why we have a -40. Minus is capacitance, the plus would be inductance. So we see this -45-ish number here. This is indicating our cable basically is now in this frequency range to where it's turned into a capacitor for the most part. Again, these are theoretical calculations, all right, done by the physicists and the like back in 1910 at Belden. So this chart goes way back. Now, the next question is, okay, great, I've seen all this theory crap. Cable doesn't really damn do that, does it? Well, I don't know. Let's take a peek. This is a open short chart of actual cable, all right? And what we're going to see here is look at our measured inductance right here. Here's our measured resistance with respect to frequency. If you look at our inductance, we're going to see that it starts at 0.125 microhenries per foot. And like I told you, it's going to drop as you go up in frequency because of that skin effect. And it does. You measure it and you see the inductance slowly ebb down to 0.11. Okay, it lost to roughly 0.01. So it's doing exactly what the theory said it should. My swept resistance, on the other hand, a lot of people are aghast that as you go up in frequency, even to 20,000 or even 15, okay, you see quite a difference in these numbers. You go from 2.27 to 3.31. Why is that? It's because of the skin effect characteristic and the proximity effect make the wires resistant look higher and higher and higher the higher you go in frequency. So this wire becomes more and more resistive as you go up in frequency. My capacitance, again, is very stable. The difference in the capacitance is just, it just kind of hangs right in there. All right, much, much flatter as far as frequency goes. Now, this capacitance was measured on a complex speaker cable on Iconoclast Series 1. So again, the capacitance does have a slight impact on the geometry of the cable made. In other words, if it's not a coax, you're not going to see the capacitance be absolutely dead flat, but for all practical purposes, it's still much, much, much more uniform percentage-wise than the inductance is going to be. Here's the impedance, all right, with respect to frequency, and notice our cable's 460 ohms. Wait a minute, isn't our speakers 4 or 8 ohms? How can we be putting a 460 ohm cable into, I have cables, they told me they were 8 ohms. That's impossible. You cannot make an 8 ohm cable, especially where most of the power is transferred, because as your velocity goes down, your impedance is driven up. You're going to see a cable that's substantially higher in measured open short impedance to the analog frequency range than our speaker is. Even if you go out in frequency, it still is 82 ohms, long shot from 4 or 8 ohms. If we look at our phase, just like the theory would predict, down here at the low frequencies, we're roughly capacitance. We go higher and higher and higher in frequency. We almost reach a point where the phase disappears. When people say they have a low phase audio cable, do you think that's true based on what you're seeing here? No, it isn't, is it? Depends on the frequency as to what you consider low phase. But trust me on this, audio cable by and large is not coherent and it's not low phase. You can improve it, but you're still going to be stuck with Mother Nature, all right, going from a capacitor towards DC and looking like the capacitance drops to nothing out here at the, or the phase goes to nothing once you reach RF, where the phase constant disappears. So you're left with square root of L over C. This was a speaker cable, by the way. Now let's look at an RCA cable. This is going to make a lot of people kind of freak out temporarily. 100 hertz. What's my impedance at 100 hertz? I didn't go lower than that because the number got so big that I figured I might make people faint if they saw the trace. 2,240 ohms, basically. People are going, whoa, wait a minute. I thought I was supposed to match an impedance. Well, remember, though, This is an RCA cable, and it theoretically goes into an infinitely high input impedance because you want it to be a voltage transfer function.
I know what an RCA connector is. What is an RCA cable?
Your RCA cable would be a coaxial design.
Coax. Okay.
Yeah. In analog, people refer to an RCA as an RCA. You're technically correct, as RCA is a type of connector that would go on a coaxial cable. But in our little world, hobbyist, I chose not to confuse people. And people say, well, I want an XLR or an RCA. An XLR actually is the name of a connector, not a cable as well.
So is this type of coax the same as used for video?
It would be similar. And you're going to see the similar effect on a coax as if you test it through analog. In other words, if you take a piece of 9259, a garden variety coax with copper conductor that was, quote, suitable for low frequency ranges, you're going to get the same general ultra high impedance up here in the 2000 plus ohm range, and you're going to see it drop down to its characteristic impedance at RF, which in case of 9259, this would be 75 ohms. And this might be somewhere in the neighborhood of 1800 ohms at 100 hertz.
So
But
this is the characteristic impedance of the RCA interconnect, RCA terminated.
yes, it is. Yeah, that's what cable really does. All right, and it's
At
because
100 hertz, really?
absolutely, it'll go much higher than this because it's logarithmic.
So-
It's going to go to infinity when it hits zero. So it'll
So
have
how is that being measured?
All right.
This is very surprising to me. So I'm curious how I could measure this at home.
Okay, well, you need to get somewhere in the neighborhood of a $40,000 or $50,000 precision RLC meter, and you can do it. The
Well,
instruments-
why would this be different from using a bridge and plugging the cable into the bridge and measuring its impedance?
because of the losses in the bridge, these measurements are incredibly touchy to get done right. All right, so depending on the accuracy of your bridge and all the switches and contacts and everything in it, you can end up with quite a bit much error. You can try it on a bridge, but you're going to see the same general phenomenon. All right, in that, again, before you get your panties in a twist about this, you have to realize this cable is theoretically going into an infinity impedance. So all the voltage is going to drop across the highest resistance in the circuit, which is out there at the end of the cable at the input resistor, which in our case is 47K ohms plus or minus.
Well, it would be the source impedance and the and
yeah, this cable
destination impedance. But I'm surprised that the characteristic impedance of the cable is so high. But you would think that for the long frequency, the low frequencies, the wavelengths would be so great that this wouldn't be a big factor.
Well, it's not
I'm
a
surprised
factor.
that the characteristic impedance is so high. That's
Well, you can't really call this a characteristic impedance straight up because, again, there's phase associated with it. All right. And generally, a characteristic impedance doesn't have a phase after it. If you look at a coax, you look at a characteristic, it's 75 ohms. It's not 75 ohms plus or minus so many degrees. You assume that the phase is zero at a true characteristic impedance. So this is really technically just called impedance because I have this phase hanging out over here associated with it. And as I go to RF, the phase goes away and I'm left with more of a characteristic impedance down here than I am up here. But since I terminate this RCA into a, in theory, infinite load, the voltage, of course, is going to drop across the largest resistance in the line. And in this case, it's out there at the end of the cable at our input to our preamp or our amplifier, because those are 47K ohms. So the signal sees 2000 ohms is still reasonably near nothing compared to 47K ohms. And if you look at it relative to the theory, which is infinity, it doesn't really matter at all. Now, why is this problem? Why does it go this high though? Because we want low capacitance on our interconnect cables. Well, when I drive my capacitance down, that makes the impedance go up. So not only is the velocity of propagation dropping at the low frequencies, VP, I'm actually designing a cable so it has a lower and lower capacitance. And that also makes the impedance go up. So two things you're doing to a cable that will make your impedance go up, not down. And the reason we can do that is because we know we're having a voltage transfer function cable. So the impedance of the cable isn't as important as the bulk capacitance value of the cable, so you do not get slew rate limiting when you're trying to transfer a voltage from one end of the cable to the other. Very different than a speaker cable where we're trying to transfer massive amounts of current. We still like to keep this number small based on the design of the cable, and there's ways to do it, all right, to get this number smaller. Here, not such a big problem. Now, when we sweep various cables and you look at the design of the overall cable, again, this is a spaghetti soup kind of measurement. I'm basically starting with a frequency on my oscillator. I increase the frequency and I literally measure the resistance milliohms for a 1 foot loop. Notice some cables start to go up dramatically. Other cables hang in there. This is basically just the Iconoclast. I designed it to be flat out to 20,000 kilohertz. This is a standard 10 gauge zip cord as an example in terms of some of the, again, remember I mentioned there's several things in the cable that are actually being changed. So you're not really hearing just the VP, you're not really hearing the impedance, you're not really hearing the swept resistance. It's all kind of superimposed one thing on top of another in analog frequency range. But we look at this general chart and we think, well, boy, I didn't know that was actually going on. And if you look at this, guys, here's right here, this starts to significantly change as low as 5,000 hertz even. So this does definitely occur during the analog frequency range for sure. So it does have an impact unless you design it to do this out here. And you have to do that by manipulating the design of the cable and the conductor size as well. So choosing your conductor size not only changes the VP characteristics, but it also changes the swept resistance across frequencies, so it's a little more coherent as well. So again, this is all kind of boiled into the overall design that you pick in terms of where this knee occurs. Have you guys seen this data before? I bet some of you guys have. I know some of you are as older, as old as me at 67. How about this? Who's this? Nelson Pass, right? Yeah, Nelson basically took a whole bunch of, at the day, back in the 1970s, cables, and he measured them. And he measured what's called swept resistance. This is the shorted measurement of the open short impedance measurement technique, by the way. So this is what would be considered half of that measurement, where you short the end of the cable and you measure the swept resistance with respect to frequency. What's interesting is my data unusual or somehow in conflict with what's been measured? Well, that would be, he did this in the 70s, so 50 years ago. No, here's 75 kilohertz roughly right here. And what do we see? We see the same kind of characteristics where some cables really take off, other cables remain flat out above 10K. This was before people understood what to do with wire though. So none of them are flat out to 20,000 kilohertz. They had no clue back in the day that they're kind of leaving some performance on the table. All right. They just used what they had and it just kind of fell where it fell. And they measured them and they didn't know why they did what they did. Some cables would sound different. They didn't really give it much thought. All right. But this is indeed what is actually happening, is you can manage this with your selection of R and the size of the conductor. And when you do that, you manage current coherence, you measure the RS value, which is used for impedance also. So again, you can, today I know what I'm doing with this. All right. Back in the day, we didn't. And that's why I said earlier on that it took me quite a couple of decades to really get a handle on what's going on with this and how to work with the swept resistance, the RS, the current coherence, and the impedance, and how to figure out a cable that sort of improves all of those things. And all cables will have variables that are going to be, they're going to vary based on the design of the cable. Physicals equals electricals in these analog cables. As certainly if this doesn't demonstrate it, I don't know what does. These are all different design cables with all different design gauge sizes, and they all behave quite differently from one another.
So when you mention size of conductor, you mean gauge sizes. You don't mean individual strand sizes.
No, they have to be individually insulated, right? The minute you lump them together like a stranded wire, that basically is the size of a 10 gauge stranded, like 1313A. Belden 10 gauge is, is highly stranded 10 gauge. But that would be seen as one solid wire, not much different from a solid 10 gauge. So your slope is going to, in other words, 1313A with a stranded wire here, if I made that a solid wire and it was still a 10 gauge, it's still going to have roughly the same exact trace. A little bit better, but not a lot. A little bit better, but certainly not like a 24 gauge or a 22 gauge here. These are roughly the same gauge size, 020 and 022. So you can see that they're the 022, okay, those slightly, you see just a small difference between the two. All right, but they're for all practical purposes, they're pretty close to the same. Now, that's why I also had to go to a 28 gauge when I designed the Series 2, because I had to make a substantial difference in the loop DCR, which also improved this RS. So it's flatter out to a higher frequency with a 28 gauge. I didn't do that specifically to flatten this because I already felt that I'm hitting my number here at 20 kilohertz quite nicely. I did it to improve this curve and move it down here. That's why I chose to use the 28 gauge. All right. Now, that actually made the capacitance go up from 45 picofarads to 75, which also helped improve this, but I didn't want to make the capacitance go up too high. All right. I still wanted to manage it reasonably well. So I wanted to do the bulk of lifting here. So a 24 gauge is 24 ohms per 1,000 feet. A 28 gauge is around 100. So I increased R about 100 ohms, which is a huge increase, whereas I only allowed the capacitance to go up half of that. So again, I wanted to do the bulk of the lifting with R. I don't want more reactance in the cable if I can avoid it. In listening tests, people felt that the change in the coherence was worth the change in capacitance, especially when those people use cables in relatively short lengths. If you used a really long cable, yes, the C would go up faster in a very long length of cable. And at some point on amplifiers that are sensitive to reactance, you can run a Series 1 longer than a Series 2, or any cable, of course, that has lower capacitance. Okay. Next, this is kind of a cool chart. And going back to what return loss is, a lot of audiophiles talk about impedance matching, all right? And remember, this is done to help determine how to better match the impedance, which I'm going to look at in just a second. But to look at what return loss is, this is basically the impedance of a 100 ohm data cable, category 5 Ethernet cable. Your return loss is a decade type response. So when you go from 10 to 20, that's a factor of 10. This is another factor of 10. This is another factor of 10. So even though this chart may look like mine, there sure is a lot of energy that's not going to the load, where you have basic, in theory, you want this to be minus infinity. This one pixel right there, that one frequency out of all the tested frequencies in this cable happened to look almost purely resistive, i.e. it's a perfect 100 ohms, and it's going to have almost no reflection off of a 100 ohm load. And the load that these Ethernet cables are terminated into is a surface mount 100 ohm resistor, literally, because they expect the cable to be theoretically square root of L over C, no phase, purely resistive. They're not. As the cable's frequencies, and each of these is an individual and separate frequency, all of these data points. But what you need to look at and realize is, notice that I can come out here and I can say, here's 110 ohms. It's not even 100, for instance. All right. And you can hit this point and you can say, I got an RL value of roughly, minus 33. But I have that same RL value when I have a cable that's 95 ohms. Why is that? Because impedance is a vector sum of the real component and the reflection coefficient. And they basically have a different real and imaginary vector, but they both measure a different vector resistance. In other words, if you were to look at the cable's vector impedance, you're going to see that they can be two different values and have the same return loss. All right. Now you come way out here. All right, and again, this is a cable that's 120 ohms, for instance, and you have the worst return loss, minus 20 dB. But again, the thing that's important to realize is this is a typical trace of an actual real Ethernet cable. And I did this chart 25 years ago when I started working with RF cables and working with RL and trying to get a handle on what is it really doing. How many frequencies really are down in here. Now this is minus 40. Remember, this is 0.010% reflected energy. This is not like these are terrible values. These are actually very small values in all things concerned. But when you look at an Ethernet cable and to believe that it's all 100 ohms resistive, like the theory says, no, it isn't. This proves pretty much that we have reactance. When the minute you go off 100 ohms, up or down, the reactance increases and your RL gets worse and worse. All right, so again, this is what happens in RF. We don't see this in analog, though, because we don't have true reflection coefficients in analog frequency range. The closest we can come is to use our open short method, all right, and calculate our impedance via the open short method. There is a way to sweep the impedance, by the way, which will give us a lot more uniform looking trace as far as what's going on than to do these charts one by one. And that's what we'll get to in just a second. Now, here's a chart that Paul McGowan did. And what this is, it's just a peak hold capture chart when he played a record. And it basically shows where's the power going as we play our music on our cables, generally speaking. Well, if you look at, this is 1,000 watts. Here's our mid-range roughly, kind of in through here. You got 15 watts. And here's our tweeter right here, only 1 watt. Well, if you look at the frequencies, this is roughly 100 hertz. Almost all of our power that's going to our speaker is going down here into low frequency range. Generally speaking, if you want to match an impedance on a piece of cable or a network, you would do it where most of the power is being distributed. Makes sense, right? You wouldn't really do it out here at the tweeter. And the impedance of a speaker is much flatter as you go up in frequency and much worse as the frequency goes down, which is opposite what we want. We'd like to see the impedance be a nice uniform 8 ohms to match into this load so we get all of this power being distributed across the speaker. But we can't do that. The reason we can't do that is here's what our impedance of our loudspeaker looks like. Out here at the high frequencies, it gets nice and uniform. Low frequencies, it's all over the place. So we're trying to measure basically a mess into a very large amount of power. We're also trying to measure it into a cable that is a very high impedance. So we have a lot of power. We have a disruptive impedance trace on just about every speaker. You might even see the best is the planar magnetics can be a little flatter down at the low frequencies, but they're still not a uniform resistive load by any means. And then you have cables that can be a zip cord, can be as high as 525 ohms. If I redesign it, I can bring this down to roughly 260 ohms. So I can make a substantial improvement in the impedance trying to match into this kind of a load, knowing full well that this is the sort of power distribution I'm talking about. All right. So these 3 things also are what you hear when you listen to a cable. What's the swept impedance of this cable look like? What kind of loudspeaker is it being terminated into? How is that aggravating the amplifier when you add this and this? And how much power are you trying to distribute into that load, and how much energy is a back EMF coming backwards into your amplifier, which is going to change the linearity of the amp. Amplifiers are measured into a pure resistive load. There is no set way to measure reactive loads in amps that would really tell you what it sounds like playing music in an audio system. So we're measuring amplifiers exactly the way we don't use them. And this is the problem. This is how we use them going into this kind of a load with this type of an impedance cable that changes with frequency, yet the amplifier is just stuck on an 8 ohm load and you're just kind of told, okay, take it or leave it. That's what it measures. Well, true, but it's not indicative of how it behaves playing music. So all of these things will interact with your amplifier because the amplifier doesn't know the difference between the cable and the speaker. It just sees it as a lump load that is quite, well, chaotic. Even if you try to optimize it, this is not 8 ohms, everybody, okay? This isn't even 8 ohms out here. And no speaker will be close to 8 ohms out here. It's physically impossible to make a true 8 ohm speaker cable because of the fact that the VP goes down, all right, when you're working in these values. Now, here's some simple measurements. This is a 1313A. Again, this is just a zip cord, 10 gauge zip cord, our standard open short impedance. And this is a series 1 and 2, and these are the impedances of those 2 different design speakers. All right, so basically you can make a substantial improvement if you pay attention to what you're doing and try to say, okay, you know, if I manipulate all these variables and I come up with designs that work, can I actually make things truly measure better? The answer is yes, you can. The next question is, well, right here, does it matter? Is that, you know, is this type of improvement going to make a difference in your system. And that's basically what all these cable designers are trying to do is, in the end, outside of sales and marketing, I don't care what you say, all these cables are going to follow the physics here that I described today. Nothing escapes it. You can manipulate it, but you can't eliminate it. Okay. So that kind of is where we conclude the presentation. I didn't add anything that specifically goes into design of the Iconoclast. I wanted the presentation to be more inclusive of what impacts all of our analog cables, not just mine, but any cable that you would pick up. I can do the same measurements, and you're going to see that they all follow the same general characteristics on these parameters. Are they differences? Yes, there are. So to say all cable measures the same is definitely not true. I'm pretty much, I think, proven that today. What does it sound like when you use it in your system? Well, it's a superposition of the coherence, the impedance, all right, skin depth, all of those things kind of superimpose one variable on top of another. You can kind of pull them out separately and look at them and see what's happening when you throw these things into this tomato sauce as far as what it might taste like. But it depends on the amplifier's load factor, driven primarily by your speaker and secondarily by the cable. So if someone were to come to me and say, well, I'm going to change my speaker cable to yours, and my speakers are going to sound like 9 times better. No, your speaker is still carrying the brunt of the impact on your amplifier's linearity. The cable can help, but by no way, means, or shape can a cable offset what a speaker load is doing to your amplifier. The cable adds to it, but it's not the majority of what you're hearing. It's going to fine tune it. Now, some amplifiers that don't have inductance on the outputs to offset the capacitance of the cable in the speaker will be more influenced by speaker cables than others. I've heard a set of Magico, the old V7s, I think they were called, a 2.5 way, huge difference when we put the Iconoclast cable in. Biggest difference I've ever heard. That was being driven by a WLA amp. I was stunned at the difference that made. Other systems, a pair of magnepans that are primarily a resistive load, which is good. I heard a difference, but we agreed that the difference was much more slight, and that's a good thing. You don't want the cable, technically, or the speaker to upset the amplifier or make much of a difference in the way it sounds. And the sound is not coming from the cable, you guys. It's not coming from the speaker. It's coming from the signal the amplifier is sending out to be played based on its reactive characteristics and how linear the amp is. We tend to think we're listening to the cable or the speaker. We're not. We're listening to what it's doing to the linearity of the amplifier when it's trying to drive this reactive of a load. All right. So the innate characteristics are still, being carried primarily by the amplifier's ability to be as linear as possible in dynamic musical response.
So can I ask a question then? Say I measure the impedance plot of my speaker. Is that going to actually help me choose the best match of a cable, or I'm just puzzling because it's the amp's reaction to the speaker cable combination, all right, that you're talking about. But I'm just trying to figure out, is there some way that I can choose, in quotes, the right cable for my amp and my speakers?
This is what it can tell you. A cable that has, this is a typical ported system where you have the 2 resonances with the saddle, they call it right here. This is what ported speakers tend to do. We see a lot of those. This level of low frequency nonlinearity will tell you this speaker will react to a speaker cable change much more so than a cable that has an impedance that would be a straight line, which would probably, here the difference would be slim to none. If you truly had a cable that was, or a speaker that was 8 ohms, boom, straight across, right here, that would say this cable, this speaker is not going to be as sensitive to a change in a cable. So in other words, when you try 4 or 5 different cables, you may find, I can't hardly tell the difference between them. If you switch to this speaker and you had 4 or 5 different cables, you may have a preference as to what cable you like better or worse. And there's the other problem. People don't like linear sound. Trust me on that. We all like a little more bass than is real. Some of us have 67-year-old ears and I turn my treble up 2 dB, so on and so forth. So what's right is still, it's a hobby. This is entertainment. The idea that Supertramp can sound the same in my basement as it does in an auditorium, that was long, lost to me years ago. All right, it's entertainment. So the sound quality is going to vary. You're going to hear a difference in the bass response primarily when you better match the impedance to the load. This is going to greatly improve how tight the bass sounds and how defining it is, less ringing in the bass, because you're pulling this impedance down, and it is a closer match. It's still not 8 ohms though, but this is going in the right direction. You want to go this way if you can, but you can't get it to 8 ohms down here. It's impossible. You can't do it. All right. The higher frequencies where things are more resistive, okay, out here, we have a lot less reflection characteristics going on and ringing than we do in the bass frequencies here. All right. You just can't escape this. This is what our hobby does. And unfortunately, this is what our power distribution looks like. All right. And this is what our cable impedance looks like. And here's our phase. Notice our phase is capacitive at the low frequencies, just like theory says. And we're going to hit basically 0 reactance out at RF. This inner area, this is that hysteresis curve, but it's backwards, right? We went 0 out here, we go high here. Whereas when we were up here, it was opposite that. We were 0 here and high there. So it's kind of an inverse version of that same curve, okay? So Mother Nature does not do things all of a sudden. And she chooses our analog frequency range right where our music is to do all this crap to us. So as a cable designer, you sort of have to be aware, do I really know I'm doing this? Do I really know I'm doing this? Well, how am I doing it and why? Where's R going? Where's C going? Did I use a huge amount of C to pull this down, or did I use more R? For instance, you don't necessarily have to use a 28 gauge wire. You can use a bigger wire and just increase the capacitance 4 or 5 times and pull this down, but that would slew rate limit, all right, the signal trying to go through the cable, which is a voltage transfer function. So you really want to keep capacitance to a bare minimum, and you want to use a passive component resistance to do the heavy lifting. All right, so all these things enter in because of the nature of our cables are, well, you know, their general nature is to not be coherent, just opposite of what is actually happening. And this is
So,
all
Galen,
quite measurable.
a question for you. For the open short method,
Yeah.
can you talk about how you did that at the audio frequencies? Because I'm familiar with the open short method with respect to sending a pulse down a transmission line and measuring its reflection value, and then from that you're able to derive the characteristic impedance of the cable. But what does it mean to do that at audio frequencies? That's something I couldn't figure out.
Yeah, I can send you the Belden test procedure on that you can read if you'd like. It's
Sure.
a little more complex than you're right. At RF, you can use what's called you can use a pulse type method at resonance on a coaxial cable to measure its impedance. So you measure the delay at 2 different frequencies, and from that you can calculate the cable's impedance. You can't do that in analog though, because we don't have a true transmission line. But yeah, I can dig out the test procedure that's used to derive all this data for you and send it to you guys. Yeah, that's
I
no big
appreciate
deal.
that.
It's
Yeah,
not a
thank you.
secret. Yeah, I was the dummy who sat down. I could not use the computerized equipment that derived the data that would give us this. This was generated by a much more sophisticated piece of equipment that's used in production. So I had to sit down and do it the hard manual method, 1 frequency at a time with an high precision LRC meter, and do this by hand. David set up the test. Now, the name Iconoclast, just to tell you funny, is when we measured this cable in terms of what it was actually doing, David said, "My God, that cable's, iconoclastic." And I'm like, "What?" He goes, "That's not tested at all like what I would think. I would think that cable would test horrible based on what it looks like. I thought the capacitance was going to be, 300 picofarads per foot. And I didn't think it would be anywhere close to as good as it is." And I said, "Well, that's the problem with designing by your eyeballs and not the data." And David's like, "I still think that's iconoclastic. That's against what I ever thought it would be." And I said, "David, you just named our product line." So that was literally how the product line was measured. As he came to my desk and said, "Galen, I think the LRC meter needs to be calibrated. It's broken." I'm like, "It is? Why?" And he says, "I'm getting these numbers and it can't be that. I'm getting like 45 puff, and I know this cable's around 300. Something's wrong with the equipment." I said, "Well, you got your reference sample, right?" So, well, let me find Carl Dole, see where we hit it. Carl found it, measured it, reference sample measured perfectly. That's when David's like, what did you do? So I explained it to David, our lab technician who measures thousands of cables a year. And he was duly impressed with what this analog cable is actually able to do as far as truly making it measurably better. So he's like, well, congratulations. I've never seen one that works as well as this. And that held true for the RCA, the speaker, and the XLR, but all using similar known characteristics of how cables really work. So none of this stuff, even down to what Nelson Pass measured, years and years ago, this is not, this isn't snake oil. I mean, I can give anybody this cable and they'll measure the same exact values that I do. So the question is, well, does a cable that measures this well, can you hear that when you put it on your speakers? And well, it depends. I don't know what your speaker's reactance is going to do through the cable and how the amplifier is going to interpret things. We all know people say certain amplifiers sound better on certain speakers, right? We hear that over and over and over again, correct? That's because amplifiers damping factor, the output damping factor, basically is the output impedance of the amp, 0.05 ohms or something like that, is divided into the load impedance, right? But the load impedance varies all over the map. So your damping factor isn't a set number, really. It's all over the place. And your damping factor, of course, affects how much that amplifier can start and stop and ring when it's playing dynamic music. So some amps, even though they look good in an 8 ohm load, when you play music on them, for some reason, when you look at the numbers between two amps, you say Julian Hirsch in the 1970s, you can't hear that. But when you put them on higher quality modern speakers, you can definitely hear that. Even though the 8 ohm resistive values and the harmonic distortion and then the IM distortion is so low, you think there's no way that that will make a difference, but it does when you play music. So the things that we can't measure on amplifiers are being influenced by some of the things we can on speaker cables and the speakers are hooked up to. So, but that's why these exist. Is I thought, well, maybe the audiophile community would like cables that are designed more of a straight up scientific method than just, pretty marketing and sales, which is what I seem to get elsewhere with no real rhyme or reason as to what's the cable, what's wrong with the cable, how are you fixing it, and how is that going to make my life better? And that's what we chose to try to do and explain. And that's kind of why I'm here today. So,
All right. Well, thank you with that. Let me see if there are any more questions.
I just had one addition to the complexity of the system, and that's the connectors. I see that the Iconoclasts are sold and you make up the connections. You don't just sell the bare cable. And so I'm assuming when you're testing these, you're testing them with the kind of connectors that you would sell them with, right? Is that correct?
That's absolutely correct. And that's something people don't appreciate. If you have a piece of coax that's 11 picofarads per foot, and you make it a foot long and you put two connectors on the end that are 2 puff per connector, that's 4 picofarads, right? That's a third of the entire capacitance of the cable. So you measure that and the customer says, I thought you said the cable was 11. I said, yeah, but you can't use it that way. You have to put a connector on it, kind of thing. So yes, all of our cables are made and tested with connectors. You get a test sheet with every cable you buy from us after it's assembled. So when you look at the data, you're actually seeing what the actual cable with connectors really does, not bulk cable. That's kind of cheating. So again, we don't do that. We test every single cable we make is tested as an assembly, test reports put in the bag with the cable. So you know what you bought, you know what it actually measured like. Is it what you expected as far as how our cables work? And all of our cables work this way, not just mine. I'm not stuck with this problem. Everybody that has a cable in your stereo, you have the exact same problems here. The variation of what's being controlled and how or why is going to vary. Yes, that's why cables sound different, but they don't escape the physics of what we've covered today. So this is really what they're doing. I think it's important to understand this. We seem to know more about amplifiers and the like than we do cables. We seem to think, well, anybody can pick up 2 conductors and a signal can reach the end, so cables must be simple. Amplifiers are a lot harder to make. Not everybody can make an amplifier that actually amplifies without making sweet smelling white smoke. So we think, well, amplifiers must be hard. Cable's hard too, because you have some variables that Mother Nature threw at us that are impacting the analog frequency range, which is of course right where our hobby exists. So no, our cables aren't coherent, not mine, not anybody's, but we can improve them. So
Well, that was very interesting and full of surprises for me. So I thank you for sharing that with us, and I would definitely be interested in the materials if you can share them afterwards.
oh yeah, it's an industry standard. Open short test is an industry standard test. Belden
Yeah.
doesn't use. It's not
Yeah.
proprietary in the least. So
Sure,
yeah,
sure.
we can share that.
I'd love to hear how that was done. Yeah, so if there are no more questions, we can conclude today's meeting. But thank you again, Galen, for the presentation. And yeah, everybody enjoy the rest of your weekend.
Super duper. Hey, thanks, Ken. Thanks for having me.
You bet.
You're
Bye.
welcome, everybody. Bye-bye.
Bye.